What shape is the universe? It sounds like a simple question. Maybe it's a sphere. Maybe it's some kind of bubble floating in something bigger. But here's the problem. The universe isn't an object sitting inside something else. There is no outside. There's no vantage point where you could float beyond the edge and look back at its shape. So what does it even mean to ask what shape it is? And here's what most people never realize. The answer to this question isn't just philosophical. The geometry of the universe controls how light travels, how galaxies move apart, whether space itself will expand forever or eventually stop. The shape of the universe determines what kind of cosmos is even physically possible. And after decades of careful measurement, physicists have found an answer, one that raises more questions than it resolves. If you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let me start with something that seems obvious. What does it mean to ask for the shape of something? In everyday life, shape is one of the simplest properties you can observe. You look at a basketball and immediately recognize it as a sphere. You pick up a book and see it's roughly a rectangular box. You glance at a dinner plate and call it a circle. Shape feels intuitive, effortless, one of the first things your brain identifies about any object. And the reason it feels so natural is that you're always observing objects from the outside. You stand apart from them. You see their boundaries. You see where they end and where something else begins. The basketball has a curved outer surface. The book has flat faces and sharp edges. The plate has a circular rim. Shape, the way we normally experience it, is something you perceive by viewing an object's boundary from a position that is not inside the object. Now try applying that same logic to the universe. You want to know its shape, so you'd need to step outside of it. Find some vantage point beyond its boundary and look back. You'd need to see where the universe ends and where something else begins. You'd need to observe its outer surface, its contour, its silhouette against whatever lies beyond. But you can't do that. And the reason isn't just that the universe is really big. It's not a matter of lacking the technology or the rocket fuel to fly far enough away. The obstacle is far more fundamental than any engineering limitation. There is no outside. The universe, by definition, is everything that physically exists. All of space, all of energy, all of matter, all of time. If you somehow managed to step outside the universe, wherever you stepped into would itself be part of the universe. You can't leave it because there's nothing to leave it for. There's no empty room that the universe sits inside of. There's no container holding it. It's not like a fish tank where you could press your face against the glass and look in from the other side. The universe isn't inside anything, and it might not have a boundary at all. Not in the way a basketball or a book or a dinner plate does. This is the first major conceptual hurdle, and it's the one that trips up almost everyone when they first encounter this question. Our intuition about shape comes entirely from objects we can view from outside. But cosmologists are asking about the shape of something that has no outside. So either the question is meaningless, or shape means something fundamentally different when you're talking about the universe. It means something different. Physicists aren't asking what the universe looks like from the outside. They're not trying to determine its silhouette or its contour or its outer boundary. They're asking about geometry. Specifically, they want to know what geometric rules space obeys on the largest possible scales. Does space behave the way your high school geometry class taught you it should? Or does it follow different rules? Rules that would change how distances work, how angles combine, how parallel lines behave, and ultimately how matter and energy move through the cosmos. To understand what this really means, you need to grasp one of the deepest insights in the history of mathematics. The insight that you can figure out the geometry of a space without ever stepping outside of it. You don't need a bird's eye view. You don't need to see the thing from above or beyond. You can determine everything about the geometry using only measurements made entirely from within. This idea sounds almost paradoxical at first. How can you know the shape of something you're trapped inside of? But mathematicians proved centuries ago that it's not only possible, it's precise. And the way they proved it starts with a deceptively simple question. What happens when you draw a triangle? Think about a triangle drawn on a flat sheet of paper. You probably remember from school that the three interior angles of any triangle always add up to 180 degrees. This feels like one of the most basic facts in all of mathematics. It's so obvious, so foundational, that it barely seems worth stating. Of course the angles add up to 180 degrees. That's just how triangles work. You learned it as a child, you used it in homework, and you probably never questioned it. Except it isn't always true. That rule holds perfectly on a flat surface. But if the surface is curved, the rule breaks. And the specific way it breaks tells you exactly what kind of curvature you're dealing with. Here's what I mean. Imagine you're standing on the surface of a perfectly smooth, perfectly round sphere. Not Earth, with all its mountains and ocean trenches and messy irregularities, but an idealized mathematical sphere, a perfect ball. Now imagine drawing a triangle on this sphere using the straightest possible lines you can draw on a curved surface. These straightest possible lines on a curved surface are called geodesics. On a sphere, geodesics are great circles, the largest circles you can draw on the sphere's surface, like the equator or lines of longitude. Start at the North Pole. Walk due south along a line of longitude, following the surface in a perfectly straight path until you reach the equator. That's the first side of your triangle. Now turn exactly 90 degrees to your left and walk along the equator. Walk along it for a while, let's say a quarter of the way around the entire equator. That's the second side. Now turn left again and walk due north along another line of longitude, straight back up to the North Pole. That's the third side. You've arrived back where you started. You've drawn a closed triangle on the surface of the sphere. Now look at the angles. At the North Pole, the two lines of longitude meet. Since you walked a quarter of the way around the equator, the angle between those two longitude lines at the pole is 90 degrees. At the first point on the equator, where you turned from walking south to walking east, the angle between the longitude line and the equator is 90 degrees. At the second point on the equator, where you turned from walking east to walking north, the angle is also 90 degrees. Add them up. 90 plus 90 plus 90 equals 270 degrees, not 180. Your triangle on the sphere has angles that sum to 90 degrees more than what flat geometry predicts. And this isn't because you made a mistake or drew the triangle incorrectly. It's because the surface itself is curved. On a positively curved surface like a sphere, triangles always have angles that add up to more than 180 degrees. The larger the triangle relative to the size of the sphere, the greater the excess. A tiny triangle on an enormous sphere will have angles very close to 180 degrees because a small patch of a big sphere looks nearly flat. But as the triangle grows, the excess becomes unmistakable. Now imagine a completely different kind of surface. Instead of a sphere, picture a saddle, the kind of shape you see on a horse's saddle, or at a mountain pass between two peaks, where the terrain curves upward in one direction and curves downward in the perpendicular direction. This kind of surface doesn't curve uniformly the way a sphere does. It curves in two opposing directions simultaneously. Mathematicians call this negative curvature. If you draw a triangle on a saddle-shaped surface using the straightest possible lines on that surface, something different happens. The angles add up to less than 180 degrees. The triangle looks slightly pinched, as if the surface is pulling its sides inward, squeezing the interior angles down. Again, A very small triangle will look nearly normal, close to 180 degrees. But a larger triangle on a saddle shows a clear deficit. The angles sum to noticeably less than 180 degrees, and on a perfectly flat surface, the one you're used to from school, the angles add up to exactly 180 degrees. No excess, no deficit. That's what flatness means in the geometric sense. It means the rules of Euclidean geometry hold exactly. Parallel lines remain parallel forever. The circumference of a circle is exactly pi times its diameter. The Pythagorean theorem works precisely. Everything behaves the way you were taught. Here is the critical realization. You can determine whether a surface is flat, positively curved, or negatively curved entirely by drawing triangles on it and measuring the angles. You never need to leave the surface. You never need to see it from above or from outside. You don't need to hover over the sphere and observe that it's round. You can figure out the curvature from within using only measurements made on the surface itself. The curvature is not something imposed from outside. It's something the surface carries within itself, something built into the way distances and angles relate to each other at every point. This idea was developed in the 1800s by some of the greatest mathematical minds in history, and it represented a genuine revolution in how humans understood geometry. For over 2,000 years, geometry meant one thing: Euclidean geometry, the system laid down by the Greek mathematician Euclid around 300 BC in his masterwork, The Elements. Euclid started with 5 postulates, basic assumptions about how points, lines, and planes behave, and from those 5 assumptions he derived an entire system of geometry. One of those postulates, the 5th one, is the famous parallel postulate. It states, in essence, that through any point not on a given line, there is exactly one line parallel to the given line. Parallel lines never meet. They stay the same distance apart forever. For centuries, mathematicians accepted Euclid's 5 postulates as self-evident truths about space. They weren't assumptions you could question. They were facts about reality. Space was flat, and Euclid's geometry described it perfectly. End of story. But in the early 1800s, mathematicians began to wonder what would happen if the parallel postulate were not true. What if, through a point not on a given line, there were no parallel lines? Or infinitely many? What kind of geometry would result? Would it be consistent? Would it make mathematical sense? Or would it immediately produce contradictions? Independently and nearly simultaneously, 3 mathematicians discovered that non-Euclidean geometries are perfectly valid. Carl Friedrich Gauss in Germany, Nikolai Lobachevsky in Russia, and János Bolyai in Hungary each showed that you could build logically consistent geometric systems where Euclid's parallel postulate does not hold. Gauss was the first to realize this, but kept his findings largely private, possibly fearing controversy. Lobachevsky and Bolyai published their work in the 1820s and 30s, showing that geometry without the parallel postulate is not nonsense. It's a perfectly coherent alternative. But Gauss went further. He proved something truly remarkable. He showed that the curvature of a surface is an intrinsic property. That word, intrinsic, is the key to everything. It means the curvature belongs to the surface itself. It doesn't depend on how the surface is embedded in a larger space. It doesn't require you to view the surface from outside. A being confined entirely to a 2-dimensional surface, a creature that could move along the surface but never lift off it, could still determine the curvature using measurements made entirely from within. Gauss considered this result so important that he called it the theorema egregium, which translates from Latin as the remarkable theorem. For a man who proved dozens of major theorems in his career, the fact that he singled this one out as remarkable tells you how profound it is. Then, in 1854, a younger mathematician named Bernhard Riemann took this idea and extended it dramatically. Riemann was a student of Gauss at the University of Göttingen and for his habilitation lecture, the presentation required to qualify as a university professor, he chose to address the foundations of geometry itself. In that single lecture, Riemann laid out a framework for describing curvature in spaces of any number of dimensions. Not just two-dimensional surfaces, but three-dimensional spaces, four-dimensional spaces, and beyond. He showed that you could define curvature, measure distances, and describe geometry in a space of arbitrary dimension without needing to embed that space inside anything larger. The space could be all there is. The curvature would still be meaningful. The geometry would still be measurable from within. Riemann was doing pure mathematics. He wasn't thinking about the universe. He wasn't trying to describe physical reality. He was exploring what geometry becomes when you abandon the assumption that space must be flat. But what he built turned out to be exactly the mathematical language that physics would need 6 decades later. In 1915, Albert Einstein published his general theory of relativity, and the mathematics he used to describe gravity was Riemann's geometry. Einstein's theory describes gravity not as a force that pulls objects toward each other across empty space, but as curvature. Mass and energy curve the fabric of space-time itself, and objects moving through that curved space-time follow the straightest available paths, which are geodesics. A planet doesn't orbit a star because a mysterious force reaches across space and tugs on it. The planet orbits because the star's mass warps the surrounding space-time into a curved geometry, and the planet follows the straightest possible trajectory through that curvature. What we perceive as the force of gravity is actually the shape of space-time telling matter how to move. This is local curvature. Around every star, every planet, every galaxy, every concentration of mass and energy, space-time is curved. Near a star, space is gently warped. Near a black hole, the warping is extreme. Even around Earth, space-time curves just enough to keep you pressed against the surface. This local curvature has been measured and confirmed to extraordinary precision. We've observed starlight bending as it passes near the Sun during eclipses, following exactly the curved path Einstein's equations predict. We've detected gravitational waves, actual ripples in the curvature of space-time caused by merging black holes billions of light years away. We've measured time running slower in stronger gravitational fields, an effect so real that GPS satellites have to correct for it continuously. Without those corrections, your phone's navigation would drift by several kilometers within a few hours. Local curvature isn't theoretical. It isn't speculative. It is one of the most rigorously confirmed ideas in all of science. But there's a completely different question lurking underneath all of this. Local curvature describes what happens around individual objects. Near a star, space-time curves one way. Near a galaxy cluster, it curves in a more complex pattern. In the vast, empty voids between galaxy clusters, space-time is nearly flat. The local geometry varies from place to place depending on what matter and energy are present. The shape of the universe is not about local curvature. The shape of the universe is about what happens when you zoom all the way out. When you average over every star, every galaxy, every cluster and void and filament in the cosmic web, what geometric rules does space follow on the largest possible scales? Is the universe, taken as a whole, flat, positively curved, negatively curved? Does it obey Euclid's rules, or does it follow one of the non-Euclidean alternatives that Gauss and Lobachevsky and Bolyai and Riemann discovered? Think of it this way. Earth's surface is covered in irregularities. There are mountains rising thousands of meters above sea level. There are ocean trenches plunging kilometers below the surface. There are plains and plateaus and volcanic ridges and continental shelves. At the local level, the terrain is bumpy, irregular, and complex. But zoom out far enough, and all those irregularities become insignificant compared to the overall curvature. At the largest scale, Earth's surface is a sphere. The bumps and dips don't change the global geometry. A mountain might be 9 kilometers tall, but compared to Earth's 13,000 kilometer diameter, that's a tiny wrinkle on a fundamentally spherical surface. The universe works the same way. At local scales, space-time is curved in complicated, lumpy ways around every concentration of mass and energy. But cosmologists believe, and observations strongly support, that at the very largest scales, averaging over billions of light years, the universe has an overall geometry, a global curvature, an average set of geometric rules that apply everywhere once you zoom out past all the local bumps. And that global geometry is what physicists mean when they ask about the shape of the universe. This question can be answered from within. Just as Gauss's imaginary creature living on a two-dimensional surface could draw triangles and measure curvature without ever leaving, we can make measurements from inside our universe to determine its large-scale geometry. We don't need to step outside. We don't need a God's eye view. We look at how light travels across billions of light years. We measure how structures distribute themselves across the cosmos. We analyze the cosmic microwave background, the oldest light in the universe. These measurements encode the geometry. They tell us what kind of space we live in. But let me be very clear about something, because this is where many popular explanations create confusion. When cosmologists use two-dimensional analogies, when they draw pictures of spheres and saddles and flat sheets, they're not claiming the universe is a two-dimensional surface. The universe has 3 dimensions of space and 1 of time. The two-dimensional analogies are pedagogical tools. They help you visualize what positive curvature and negative curvature mean in terms you can picture. A sphere is something you can see and hold and understand. A 3-dimensional, positively curved space is not something you can easily picture because you'd need a 4th spatial dimension to see it from outside. The analogy works for conveying the concept, but it breaks down if you take it too literally. In flat 3-dimensional space, all the rules of Euclidean geometry hold exactly. Parallel light beams stay parallel. Triangles have angles summing to 180 degrees. The volume of a sphere grows with the cube of its radius. Everything works the way your textbook says. In positively curved 3-dimensional space, parallel light beams slowly converge. Triangles have angle sums exceeding 180 degrees, and if you travelled far enough in a perfectly straight line, you'd eventually return to your starting point. Not because you travelled in a circle, but because space itself curves back on itself, just like walking in a straight line on Earth's surface eventually brings you back to where you started. In negatively curved 3-dimensional space, parallel light beams gradually diverge. Triangles have angle sums less than 180 degrees. Space spreads out faster than Euclidean geometry predicts, opening up in every direction. Now, here's something important that most popular accounts leave out entirely. The curvature we're discussing, the large-scale geometry of the universe, is not something you could observe by looking at the arrangement of galaxies in the night sky. It doesn't mean galaxies are laid out in a spherical pattern or a saddle pattern. The curvature is a property of space itself, not a pattern in the distribution of objects within space. 2 beams of light starting out perfectly parallel might converge or diverge over cosmic distances depending on the curvature. But you would never notice this effect in your living room, across your city, or even across the entire solar system. The curvature is so subtle that it only reveals itself across distances of billions of light years, where its cumulative effect finally becomes large enough to measure. This is why the question took so long to answer. Even after the mathematical framework existed, even after Einstein showed that space-time curvature is real, it took most of the 20th century to develop instruments sensitive enough to detect the universe's global geometry. There's one more distinction worth emphasizing before we move on, because it is a source of enormous confusion. The shape of the universe is not the same question as whether the universe has an edge. People hear the word shape and immediately picture something like a ball floating in empty space, with a clear inside and outside and a definite boundary. That mental picture is completely wrong for the universe. A universe could be flat and infinite, stretching endlessly in all directions with no boundary anywhere. A universe could be positively curved and finite in volume, wrapping around on itself the way the surface of a sphere does. Finite, but without any edge or boundary. A universe could even be flat and still finite if it has the right kind of topology, connecting back on itself in a way that doesn't involve curvature at all, like a video game screen where going off the right side brings you back on the left. The shape of the universe refers entirely to its internal geometry, the rules that govern distances, angles, and volumes on the largest scales. It's not about an external silhouette. It's not about edges or containers. There is no container. There is no outside. There's just space, following geometric rules that we can measure and describe. You might wonder why any of this matters. If the curvature only shows up across billions of light years, if it has zero effect on your daily life, or even on the behavior of our entire solar system, why should anyone care? Because the geometry of the universe is not decorative. It's functional. The large-scale shape of space determines how the universe expands. It determines whether expansion will continue forever or eventually reverse and collapse. It affects how structures like galaxies and galaxy clusters form and evolve over billions of years. It constrains what happened in the earliest moments after the Big Bang and limits what can happen in the far future. The shape of the universe determines what kind of cosmos is physically possible and what kind of cosmic destiny awaits everything within it. Think of it like the shape of a road. A flat road, a road curving uphill, and a road curving downhill all lead to very different journeys, even if the car driving on them is identical. The geometry of the road determines the trajectory, and the geometry of the universe determines the trajectory of everything in it, including light, including galaxies, including us. So, here's where we stand. The shape of the universe isn't about what it looks like from outside. It's about the internal geometry of space on the largest possible scales. It can be measured from within using observations of light and matter spanning billions of light years. It comes in three fundamental possibilities: flat, positively curved, or negatively curved. And it matters enormously because geometry controls how the universe expands, how structures form, and what kinds of futures are physically allowed. The next question is what each of those three geometries actually means in concrete, physical terms, how they differ from one another in ways you can measure, and how one single number, determined by everything the universe contains, decides which geometry we actually live in. So the universe has a geometry, an internal set of rules governing how space behaves on the largest possible scales. And we've established that physicists can determine geometry from within without ever stepping outside, using measurements of light and matter stretched across billions of light years. Now comes the next question. What are the actual options? What are the possible geometries the universe could have? And how does each one change the physical behavior of space in concrete, measurable ways? The answer is surprisingly constrained. There are only three fundamental possibilities. The universe on the largest scales can be flat, positively curved, or negatively curved. That's it. Those are the only geometries consistent with a universe that looks roughly the same everywhere and in every direction. A universe that is homogeneous and isotropic. And each of these three options leads to a completely different set of physical consequences. Different behaviors for light, different relationships between distance and volume, different answers to the most basic questions about what happens when you try to travel in a straight line through the cosmos. Let's start with flat space, because it's the most familiar. Flat space is the geometry you learned about in school, even if nobody called it that. It's Euclidean geometry, the geometry of flat surfaces, straight rulers, and simple grids. In flat space, all the rules of classical geometry hold exactly. Parallel lines stay parallel forever. You can extend two perfectly parallel light beams across the entire observable universe, and they'll remain the same distance apart from start to finish, never converging, never diverging. Triangles have interior angles that sum to exactly 180 degrees, no matter how large or small the triangle is. The ratio of a circle's circumference to its diameter is exactly pi. The volume enclosed within a sphere of radius r grows exactly as 4/3 times pi times r cubed. Everything works the way your mathematical intuition says it should. In a flat universe, there are no surprises built into the fabric of space itself. Space doesn't pull things together or push things apart simply by virtue of its geometry. If you placed two objects at rest relative to each other in a perfectly empty, flat universe with no mass, no energy, nothing to create any forces, those objects would stay at rest relative to each other forever. The geometry alone doesn't create any tendency to move. This is the simplest possible geometry, the default setting, if you want to think of it that way. And while simplicity doesn't prove anything, flat geometry does have a special mathematical status. It sits precisely on the boundary between the other two options. Now consider a positively curved universe. This is harder to picture because your everyday visual experience doesn't include three-dimensional curved spaces. So let's lean on the two-dimensional analogy for a moment, carefully, knowing that it has limits. Think about the surface of a sphere, the surface of a basketball, or better yet, the surface of a perfectly smooth globe. This surface is two-dimensional. A tiny ant walking on that surface can only move in two directions, north-south and east-west. The ant can't move up off the surface or down into it. Its entire existence is confined to the two-dimensional curved surface. Now, this surface has a very specific property. It curves the same way everywhere. No matter where the ant stands on the sphere, the local geometry is identical. Every point on a perfect sphere has the same curvature. The surface is homogeneous and isotropic, the same everywhere and the same in every direction, at least locally. On this positively curved surface, geometry behaves differently from flat space. We've already seen that triangles have angles summing to more than 180 degrees. But there's more. Parallel lines don't exist. On a sphere, every pair of geodesics, the straightest possible lines on the surface, eventually intersects. Think about lines of longitude on a globe. They all appear parallel at the equator, crossing it at right angles, evenly spaced. But follow them toward either pole and they all converge. They all meet at the same point. On a sphere, you cannot draw two straight lines that remain the same distance apart forever. Every pair of straight lines eventually meets. There's another remarkable property. If you start at any point on the surface of a sphere and walk in a perfectly straight line, a geodesic, you don't go on forever. Eventually, you come back to where you started. The surface is finite. It has a definite total area. But it has no edge. There's no boundary, no wall, no place where the surface ends. You can walk forever without hitting an edge, but you'll keep returning to places you've already been. It's finite, but unbounded. Now translate this, carefully, into 3 dimensions. A positively curved three-dimensional universe would behave the same way, just with an extra dimension. Two beams of light that start out perfectly parallel would slowly converge. They wouldn't stay parallel. Space itself would bend them toward each other, gently pulling them closer over vast distances. A triangle drawn with light beams across billions of light years would have angles summing to more than 180 degrees. The volume enclosed within a sphere of a given radius would be less than what Euclidean geometry predicts, because space itself curves inward, leaving slightly less room than you'd expect. And if you could somehow travel in a perfectly straight line, a geodesic, through a positively curved universe without stopping, you wouldn't go on forever. Eventually, after an unimaginably long journey, you'd return to your starting point. Not because you curved or turned, because space itself wraps around. The universe would be finite in volume, containing only so much space, but it would have no edge, no boundary, no wall. You could never reach the end of it because there is no end. It simply connects back to itself, the way the surface of a sphere connects back to itself, but in 3 dimensions instead of 2. This is a genuinely strange concept. A space that is finite but has no boundary is hard to visualize because every finite thing in your daily experience has edges. A room has walls, a swimming pool has sides, a country has borders. But a positively curved universe doesn't. It's finite the way the surface of a sphere is finite. There's only so much of it, but there's no place where it stops. Now the third option, negative curvature. This one is even harder to picture, and the 2-dimensional analogy is less clean, but it's still useful. The classic 2-dimensional surface with uniform negative curvature is a saddle shape. Imagine the shape you see at the lowest point of a mountain pass, where the terrain curves upward in one direction toward the peaks, and downward in the perpendicular direction into the valleys. That shape, where the surface curves in opposite directions simultaneously, is negatively curved. But there's a problem with the saddle analogy. A saddle has uniform negative curvature only at a single point or in a small region. To make an entire surface with uniform negative curvature everywhere, you'd need a shape that extends outward and keeps flaring open wider and wider forever. The technical term for this is a hyperbolic surface, and it's genuinely difficult to visualize because it doesn't embed neatly into flat 3-dimensional space the way a sphere does. Hyperbolic surfaces ripple and spread. If you've ever seen a piece of coral or a crinkled lettuce leaf, you've seen something that approximates a small patch of hyperbolic geometry, where there's more surface area crammed into a given region than flat geometry would predict. On a negatively curved surface, geometry goes the opposite direction from positive curvature. Triangles have angles that sum to less than 180 degrees. The angles appear pinched, as if the surface is pulling the sides apart. Parallel lines diverge. 2 geodesics that start out parallel, traveling side by side in the same direction, gradually spread apart as they extend. They separate, moving farther and farther from each other. There are infinitely many lines through a given point that are parallel to a given line, in the sense that they never intersect it, because lines have room to spread out in ways that flat geometry doesn't allow. And the volume enclosed within a sphere of a given radius is more than what Euclidean geometry predicts. Negatively curved space spreads out faster than flat space. It opens up. There's more room in it than you'd expect. A sphere drawn in negatively curved space contains more volume than the same sphere drawn in flat space. The space itself is generous, expanding outward in every direction beyond what flatness would allow. Translating this to a 3-dimensional negatively curved universe, 2 parallel light beams would slowly diverge. A triangle made of light spanning cosmic distances would show angles summing to less than 180 degrees. And if you travelled in a straight line, you would go on forever. you'd never return to your starting point. The space opens up endlessly, infinite in extent, with more room at every scale than Euclidean geometry predicts. A negatively curved universe is open. It stretches on without limit, and straight lines extend forever without closing back. So those are the three options. Flat space, where geometry is Euclidean, parallel lines stay parallel, and everything works the way your textbook says. Positively curved space, where parallel lines converge, triangles have excess angle sums, and the universe could be finite but without boundary. A negatively curved space, where parallel lines diverge, triangles have reduced angle sums, and the universe stretches outward without end. But here's where we need to be extremely careful about the two-dimensional analogies, because they can mislead in a very specific and damaging way. When you picture a sphere, you naturally picture it sitting in three-dimensional space. You see the ball, you see the inside, you see the outside. The curvature seems to exist because the surface is embedded in a larger, higher dimensional space. The sphere's surface curves because it's bending through the third dimension. This makes it tempting to think that if the three-dimensional universe is positively curved, it must be curving through some fourth spatial dimension. It must be a three-dimensional surface embedded in a four-dimensional space, the way a two-dimensional sphere is embedded in three-dimensional space. That's wrong, or at least it's not required. Curvature, as Gauss and Riemann showed, is intrinsic. It doesn't need a higher dimensional space to curve into. The geometry can be measured entirely from within. The universe doesn't need to be bending through a fourth spatial dimension to be positively curved. The curvature is a property of the space itself, not a consequence of embedding. This is one of the most important and most frequently misunderstood points in all of cosmology. The universe is not sitting inside something larger. The curvature is internal, self-contained, and fully described by how distances and angles work within the universe's own three dimensions. The two-dimensional analogies are useful for building intuition, but you have to remember they're showing you an intrinsic property, curvature, using a picture that accidentally makes it look like an extrinsic property, bending through a higher dimension. The bending is an artifact of the picture, not a feature of the physics. Now comes a crucial question. Which geometry does our universe actually have? And what determines the answer? This is where physics enters the picture. The geometry of the universe isn't a random fact or an arbitrary choice. It's determined by the contents of the universe, by how much energy and matter are present. Einstein's equations of general relativity, the equations describing how mass and energy curve spacetime, connect the universe's geometry directly to its density, how much stuff is packed into each cubic unit of space. In the 1920s, just a few years after Einstein published general relativity, a Russian physicist named Alexander Friedmann derived the first solutions to Einstein's equations for a universe that is homogeneous and isotropic, the same everywhere and the same in every direction. Friedmann wasn't describing some exotic theoretical scenario. He was describing what the universe looks like when you average over all the local lumps and bumps, all the individual galaxies and clusters, and focus on the large-scale average. His solutions showed something striking. The geometry of the universe, whether it's flat, positively curved, or negatively curved, depends on a single number. That number is the density of the universe compared to a specific value called the critical density. Critical density is a very specific energy density. It's the exact density at which the universe is perfectly flat, right on the boundary between positive and negative curvature. You can think of it as a balancing point. If the actual density of the universe equals the critical density, space is flat. If the actual density exceeds the critical density, there's more energy and matter than the flat case, and the extra gravitational influence curves space positively. the universe closes in on itself. If the actual density is less than the critical density, there's less energy and matter than the flat case, and space curves negatively. The universe opens outward. Cosmologists express this relationship using a parameter called omega. Omega is defined as the ratio of the universe's actual density to the critical density. It's a dimensionless number, just a ratio, and it encodes everything about the universe's large-scale geometry. If omega equals exactly 1, the actual density matches the critical density perfectly, and the universe is flat. Euclidean geometry holds on the largest scales. Parallel lines stay parallel. The universe might be infinite in extent, stretching on forever in every direction. If omega is greater than 1, the actual density exceeds the critical density, and the universe is positively curved. Parallel lines converge. Triangles have excess angles. The universe might be finite but unbounded, wrapping back on itself. The larger omega is above 1, the more strongly the universe curves, and the smaller its total volume. Much like a sphere with more curvature, has a smaller radius and less surface area. If omega is less than 1, the actual density is below the critical density, and the universe is negatively curved. Parallel lines diverge. Triangles have deficit angles. The universe is open and infinite, spreading outward without limit. The farther omega is below 1, the more strongly space curves open. This relationship, this connection between the total energy content and the shape of space, is one of the most elegant and consequential results in all of cosmology. It tells you that the geometry of the universe is not some abstract mathematical curiosity. It's a direct physical consequence of what the universe contains. The total amount of matter, radiation, dark matter, dark energy, everything that contributes to the energy density of the cosmos, all of it feeds into this single ratio, and that ratio determines the curvature. But why should density determine geometry? What's the physical connection between how much stuff the universe contains and whether space is flat, curved inward, or curved outward? The link comes from a competition, a tug-of-war that has been going on since the universe began. On one side is expansion. The universe is expanding. Space is stretching, carrying galaxies apart. This expansion has kinetic energy. You can think of it as the universe's outward momentum, the tendency of everything to keep flying apart. On the other side is gravity. All the matter and energy in the universe pulls on everything else, trying to slow the expansion down, trying to pull everything back together. Gravity works against expansion the same way Earth's gravity works against a ball thrown upward. The ball rises, slowing down as gravity pulls it back. The critical density is the exact balance point in this tug-of-war. It's the precise amount of energy and matter where the gravitational pull exactly matches the kinetic energy of expansion. Not enough to halt it, not so little that expansion runs away unopposed. Perfectly balanced. If the actual density exceeds the critical density, gravity is winning. There's more gravitational pull than the expansion can resist in the long run. This excess gravitational influence curves space positively, bending it inward, closing it on itself. The geometry reflects the fact that gravity has the upper hand. Space curves the way it does because the contents are heavy enough to dominate. If the actual density is less than the critical density, expansion is winning. There isn't enough gravitational pull to match the outward momentum. The universe flies apart more freely than the balanced case. This deficit curves space negatively, opening it outward. The geometry reflects the dominance of expansion over gravity. Space spreads faster than it would in the balanced case, because there isn't enough matter to hold it back. And if the actual density exactly equals the critical density, neither side wins. The tug-of-war is perfectly balanced. Gravity slows the expansion, but never enough to reverse it. expansion continues, but never runs away unchecked. Space doesn't curve inward or outward, it remains flat. The geometry reflects the perfect balance between the two competing tendencies. This is why geometry and density are linked. The curvature of space isn't determined by some separate mechanism. It's a direct expression of the balance between gravitational attraction and the kinetic energy of cosmic expansion. The shape of space is the scoreboard of a contest that has been playing out since the first moment of the universe. A contest between the pull of everything in the cosmos and the outward momentum of space itself. And the score, the outcome of that contest, is written into the geometry everywhere you look. Now, what counts as density in this calculation? Everything. Ordinary matter, the atoms that make up stars and planets and people, contributes to the density. Dark matter, the invisible substance that outweighs ordinary matter by about 5:1, contributes to the density. Radiation, photons and neutrinos streaming through space, contributes. And dark energy, the mysterious component that makes up about 68% of the universe's total energy budget, contributes. Each of these components affects the universe differently. Ordinary matter and dark matter slow down the expansion of the universe through gravitational attraction. Radiation does the same, though it becomes less important as the universe expands, because radiation gets diluted and redshifted. Dark energy does something completely different. It accelerates the expansion, pushing space apart faster and faster over time. But when it comes to determining the geometry, what matters is the total. Add up all the energy density from every source, compare it to the critical density, and you get omega. That single number, that single ratio, tells you the shape of space. The critical density itself has a specific value that depends on the current expansion rate of the universe, a number called the Hubble constant. Using the current best measurements, the critical density is approximately 9.5 times 10 to the negative 27 kilograms per cubic meter. That's an astonishingly small number. It corresponds to roughly 6 hydrogen atoms per cubic meter of space. That's how little density is needed to make the universe flat. On average, space is incredibly empty. But even that tiny density, spread across the entire volume of the cosmos, adds up to an enormous total. And it's the ratio of the actual density to this critical value that determines everything about the large-scale geometry. Let me say something about why this matters physically, beyond just knowing whether lines converge or diverge. Because the geometry of the universe doesn't just determine abstract geometric properties, it determines how the universe responds to its own contents. It affects how expansion behaves over time. It constrains the relationship between what the universe looks like now and what it will look like in the far future. In a positively curved universe, with omega greater than 1 and no dark energy, the gravitational pull of all that extra density eventually wins. The expansion of the universe slows down, comes to a halt, and then reverses. The universe begins to contract. Space starts collapsing. Galaxies that were moving apart begin moving together. The temperature rises. Everything that had been spreading out for billions of years starts crashing back inward. Eventually, all the matter and energy in the universe would come together in a catastrophic collapse, sometimes called the Big Crunch. The geometry dictates this outcome. Positive curvature means the universe wraps around itself, and the extra density provides enough gravitational pull to eventually halt and reverse the expansion. In a negatively curved universe with omega less than 1 and no dark energy, the opposite happens. There isn't enough density to slow the expansion to a halt. The universe keeps expanding forever. As it expands, the density drops. Matter spreads thinner and thinner. Stars eventually burn out, galaxies drift apart, and the universe becomes increasingly cold, dark, and empty over the eons. The expansion never reverses. It just continues, slowing down, but never stopping. The geometry dictates this too. Negative curvature means the universe is open, infinite, and its contents are too sparse to pull space back together. And in a flat universe with omega exactly equal to 1 and no dark energy, you get the knife edge case. The expansion slows down forever, but never quite comes to a halt. The universe approaches a state of zero expansion rate asymptotically, getting closer and closer to stopping, but never actually reaching zero. It's balanced perfectly between the collapsing and the endlessly expanding scenarios. You can see why the geometry matters. It's not a decorative label. It's the difference between a universe that eventually collapses, a universe that expands forever, and a universe that balances on the boundary between those two fates. The shape of space, determined by how much energy it contains, directly controls the cosmic trajectory. Now, I need to add an important nuance here. Everything I just described, the clean relationship between geometry and fate, applies in a universe where the dominant forms of energy are matter and radiation, things whose gravitational influence slows expansion down. For most of the 20th century, cosmologists assumed this was the case. They assumed the universe contained ordinary matter, dark matter, radiation, and nothing else of consequence. And in that framework, the geometry-fate connection is straightforward. Flat means balanced on the knife edge. Closed means eventual collapse. Open means eternal expansion. But the discovery in 1998 that the expansion of the universe is accelerating, not decelerating, changed this picture dramatically. The cause of this acceleration is something called dark energy. Dark energy behaves nothing like matter or radiation. Instead of slowing expansion through gravitational attraction, dark energy drives expansion faster. It acts like a kind of repulsive influence woven into the fabric of space itself, and the more space there is, the more dark energy there is, because dark energy has an approximately constant energy density per unit volume. As the universe expands and creates more volume, the total amount of dark energy increases. This creates a runaway effect. More space means more dark energy. More dark energy means faster expansion. Faster expansion means more space. And the cycle feeds itself. Dark energy complicates the simple geometry-fate connection. In a universe with dark energy, a flat universe doesn't hover on the knife edge, it accelerates. A positively curved universe doesn't necessarily recollapse. If there's enough dark energy, it can overpower the gravitational pull of the extra density and drive the universe into eternal accelerating expansion anyway. Geometry still matters, but it's no longer the sole determining factor. You have to account for both the geometry and the composition, both the curvature and the nature of the energy filling space. In our universe, both factors are at play. The geometry is very close to flat, as we'll discuss in detail shortly, and dark energy makes up roughly 68% of the total energy budget. The combination of near-perfect flatness and dominant dark energy means our universe is not merely expanding, it's expanding at an accelerating rate, and will almost certainly continue doing so forever. Not because the geometry demands eternal expansion, as in the open negatively curved case, but because dark energy pushes so hard that nothing can stop it. Still, the geometry matters profoundly. Even in the presence of dark energy, the curvature determines how light travels across cosmic distances, how we interpret the cosmic microwave background, and how we reconstruct the history of expansion from the distribution of galaxies. Geometry is the lens through which all of cosmology is interpreted. Change the geometry, and every measurement, every distance, every age estimate for every object in the cosmos shifts with it. There's one more aspect of these three geometries that deserves attention, and it concerns what they imply about the universe's spatial extent. In a flat or negatively curved universe, the simplest interpretation is that space is infinite. It stretches on forever in every direction without limit. There's no boundary, no edge, and no largest possible distance. You can always go farther. In a positively curved universe, space can be finite, wrapping around on itself, with a definite total volume but no boundary. This doesn't mean there's a wall at the edge. It means space connects back to itself like the surface of a sphere, just in 3 dimensions. But here's something most people don't realize. The relationship between curvature and spatial extent isn't as rigid as it first appears. It is possible, mathematically, for a flat universe to be finite, and it is possible for a positively curved universe to behave in ways that complicate the simple picture. The curvature tells you about the local geometric rules, but the overall structure, whether the universe wraps around on itself or extends forever, depends on something called topology, which is a separate question from curvature. We'll return to this later, because it has implications that are both beautiful and deeply unsettling. For now, what you need to hold on to is this. The universe has 3 possible large-scale geometries: flat, positively curved, and negatively curved. Each one leads to fundamentally different physical behaviors. The geometry is determined by the total energy density of the universe compared to the critical density, encoded in the single parameter omega. And the geometry is not just an abstract label. It controls how light travels, how structures form, how expansion proceeds, and ultimately, what kind of future is possible. The question of which geometry we actually live in is not theoretical idle curiosity. It's one of the most consequential measurements in all of science. And for decades, cosmologists poured enormous effort into nailing down the answer. The next step is understanding why the geometry matters beyond expansion alone, how it connects to the cosmic microwave background, how it shapes the large-scale structure of everything we can see, and what the discovery of dark energy did to the simple picture of geometry controlling destiny. Because the geometry of the universe isn't just a number, it's the operating system of the cosmos. Everything that has ever happened and everything that ever will happen plays out on a stage whose geometric rules are written by the density of everything it contains. So the universe has 3 possible large-scale geometries: flat, positively curved, negatively curved, and the geometry is determined by the total energy density compared to the critical density. But knowing the options isn't enough. The real question is why any of this matters beyond geometry for its own sake. Why should the curvature of space on scales of billions of light years matter to physics, to cosmology, or to anything at all? The answer is that geometry is not passive. It's not a backdrop. It's an active participant in the physics of the universe. Geometry determines how light moves across cosmic distances. It determines how we interpret the size and age of distant objects. It governs the formation of the largest structures in the cosmos, and it leaves a direct, measurable imprint on the oldest light in the universe. Light that has been travelling through space for nearly 13.8 billion years. The geometry of space is written into the data. Every observation we make of the distant universe is filtered through the lens of curvature. If we get the geometry wrong, every conclusion we draw about the history and contents and fate of the cosmos would be wrong too. Let's start with light. Light travels along geodesics, the straightest possible paths through curved space-time. In flat space, a geodesic is what you'd call a straight line. Light goes from point A to point B along the shortest path, which is also the straightest path, and that path is exactly what Euclidean geometry predicts. But in curved space, geodesics aren't straight in the Euclidean sense. They follow the curvature. In positively curved space, geodesics gently converge. Light beams that start out parallel gradually bend toward each other. In negatively curved space, geodesics diverge. Parallel light beams spread apart. This has an immediate and measurable consequence for how distant objects appear. Consider a galaxy very far away, billions of light years from Earth. The light from that galaxy has been traveling through space for billions of years to reach us. During that journey, the light follows a geodesic through the universe's geometry. If the universe is positively curved, the converging geodesics act somewhat like a lens. They bend the light paths inward, which makes the distant galaxy appear larger than it would in flat space. The object takes up more of the sky than flat geometry predicts. It's as if space is magnifying distant objects, spreading their images out because the converging geometry funnels light toward the observer from a wider area. In negatively curved space, the effect reverses. Diverging geodesics spread the light paths apart, making distant objects appear smaller and farther away than flat geometry predicts. The negative curvature thins out the appearance of distant objects, compressing their images because light from different parts of the object spreads out more during the journey. In flat space, the apparent size of a distant object follows the familiar inverse relationship with distance. Something twice as far away looks half as big. This is the relationship your eyes are calibrated for in everyday life. These differences aren't abstract, they're measurable. Astronomers observe distant objects constantly, measuring their apparent sizes and brightnesses. To interpret those measurements correctly, to determine how far away a galaxy actually is, how large it actually is, how luminous it actually is, you need to know the geometry of the space the light traveled through. Different geometries give different answers to all of these questions. A galaxy that appears a certain size in the sky could be at very different distances depending on whether the universe is flat, positively curved, or negatively curved. The geometry is embedded in every measurement of every distant object. Now let's talk about something more specific and more powerful. The single most important observational tool for determining the geometry of the universe is the cosmic microwave background, often abbreviated as the CMB. The cosmic microwave background is the oldest light in the universe. It was emitted about 380,000 years after the Big Bang, at a moment called recombination. Before recombination, the universe was so hot and dense that atoms couldn't exist. Electrons and protons were separate, forming a plasma that was opaque to light. Photons couldn't travel far before colliding with a free electron and scattering in a random direction. The universe was foggy, filled with light that couldn't move freely. But as the universe expanded, it cooled, and about 380,000 years after the Big Bang, the temperature dropped below roughly 3,000 degrees. At that temperature, electrons and protons could finally combine to form neutral hydrogen atoms. Neutral atoms are transparent to most wavelengths of light, so suddenly, in a relatively brief window of time, the universe went from opaque to transparent. Photons that had been trapped in the plasma were released. They streamed outward in every direction and have been traveling through space ever since. Those photons are the cosmic microwave background. They've been traveling for nearly 13.8 billion years, stretched by the expansion of space from their original high-energy wavelengths to the microwave part of the spectrum. When we observe the CMB today, we're looking at the universe as it was 380,000 years after the Big Bang. We're seeing the surface of last scattering, the moment when light was released from the primordial plasma. And that surface carries information about the conditions in the early universe. Specifically, it carries information about the density variations in the plasma at the time of recombination. The early universe wasn't perfectly uniform. There were tiny fluctuations in density. Some regions were slightly denser than average, others slightly less dense. These density fluctuations created pressure waves, essentially sound waves, traveling through the plasma. The denser regions were slightly hotter, and the less dense regions were slightly cooler. When recombination happened and the photons were released, those temperature differences were frozen into the light. The CMB carries a map of those hot and cold spots, a snapshot of the universe's density pattern at 380,000 years old. Now here is where geometry enters. Those density fluctuations had a characteristic size. The physics of the early universe determines how large the dominant fluctuations should be in real physical terms, measured in light years or megaparsecs. We can calculate this size from first principles using well-understood physics, the speed of sound in the primordial plasma, the time available for sound waves to travel before recombination, and the composition of the universe at that epoch. The result is a specific physical length, roughly 450,000 light-years across at the time of recombination. The question is, how large do those fluctuations appear in the sky when we observe the CMB today? We know their physical size. We know their distance, how far away the surface of last scattering is. And so the apparent angular size we observe depends entirely on the geometry of the space the light travelled through to reach us. In a flat universe, the light travels along straight geodesics, and the angular size of the dominant fluctuations comes out to about 1 degree on the sky. That's the prediction of flat geometry. If you look at the CMB and the biggest hot and cold spots are about 1 degree across, the universe is flat. In a positively curved universe, the converging geodesics magnify the fluctuations. The same physical structures would appear larger than 1 degree on the sky. The hot and cold spots would look bigger than flat geometry predicts. In a negatively curved universe, the diverging geodesics shrink the fluctuations. The same physical structures would appear smaller than 1 degree. The hot and cold spots would look smaller than flat geometry predicts. This is an extraordinarily clean test. You have a known physical size. You have a known distance. The apparent angular size tells you the geometry. It's like placing a ruler of known length at a known distance and seeing how big it looks. If it looks bigger than expected, space is positively curved. Smaller than expected, negatively curved. Exactly the expected size, flat. The first strong measurements came from a NASA satellite called COBE, the Cosmic Background Explorer, launched in 1989. COBE confirmed that the CMB exists as a nearly perfect thermal spectrum and detected the tiny temperature fluctuations for the first time. But COBE didn't have the angular resolution to precisely measure the size of the dominant fluctuations. It could see that they existed, but couldn't sharply resolve their structure. The breakthrough came with a successor satellite called WMAP, the Wilkinson Microwave Anisotropy Probe, launched in 2001. WMAP mapped the entire sky in microwave light with much higher resolution than COBE. It measured the angular sizes of the CMB fluctuations with precision that had never been achieved before. And the result was striking. The dominant fluctuations are about 1 degree across, exactly what flat geometry predicts. This was confirmed and refined further by the European Space Agency's Planck satellite, launched in 2009, which mapped the CMB with even greater precision. Planck's measurements show that the universe is flat to within roughly 1/5%. The parameter omega, the ratio of actual density to critical density, is measured to be 1.000 plus or minus 0.002. That's extraordinarily close to exactly 1. The universe, as far as we can measure, is flat, not positively curved, not negatively curved, flat. But the CMB tells us more than just the curvature. The detailed pattern of hot and cold spots, their statistical properties, the way fluctuations of different sizes relate to each other, all of this carries information about the composition of the universe. By analysing the full pattern, Cosmologists have determined that ordinary matter makes up about 5% of the total energy density. Dark matter makes up about 27%, and dark energy makes up about 68%. These three components together add up to the critical density, which is why the universe is flat. Each component leaves a different imprint on the CMB pattern. The relative heights and positions of the peaks in the angular power spectrum, a statistical description of how much structure exists at each angular scale, encode the ratios of these components. Ordinary matter affects the peaks one way, dark matter affects them differently. Dark energy primarily affects the largest angular scales. By fitting a theoretical model to the observed pattern, cosmologists can extract all three values simultaneously, along with other parameters like the age of the universe, the expansion rate, and the overall geometry. This is why the CMB has been called the Rosetta Stone of cosmology. It encodes nearly everything about the universe's large-scale properties into a single observable, the pattern of temperature fluctuations in the oldest light. And the geometry, the curvature, the shape of space, is woven into that pattern through the angular sizes of the fluctuations. Now let's connect geometry to something else: large-scale structure. The distribution of galaxies across the cosmos. Those density fluctuations in the early universe, the same ones imprinted in the CMB, are the seeds of all the structure we see today. Regions that were slightly denser than average in the primordial plasma attracted more matter through gravity over time. They grew denser still. Less dense regions lost matter to their surroundings, becoming emptier. Over hundreds of millions of years, the denser regions collapsed to form the first galaxies and galaxy clusters. The less dense regions became the cosmic voids, enormous regions of nearly empty space stretching hundreds of millions of light-years across. The result is the cosmic web, a vast network of filaments and walls of galaxies surrounding enormous voids. Galaxies aren't scattered randomly through space. They trace out a web-like pattern, with dense clusters at the intersections of filaments and nearly empty voids in between. This structure exists on scales of hundreds of millions of light-years, and its statistical properties carry information about the geometry and composition of the universe. Here's why. The same sound waves that created the fluctuations in the CMB also left a signature in the distribution of matter. Before recombination, pressure waves traveled through the plasma, creating regions of compression and rarefaction. When recombination happened, those waves froze in place. The matter that had been part of those waves kept the pattern imprinted on it. Over billions of years, this pattern evolved under gravity, but its fundamental scale, the distance the sound waves traveled before freezing, was preserved. This characteristic scale is called the baryon acoustic oscillation scale, and it's about 490 million light-years in today's universe, stretched from the original 450,000 light-years by the expansion of space over 13.8 billion years. It's a cosmic ruler built into the distribution of galaxies. Galaxies are statistically more likely to be separated by this distance than by slightly larger or smaller distances. It's a subtle effect, a slight excess in the number of galaxy pairs at this separation, but it's been measured in large galaxy surveys with high confidence. And just like the CMB fluctuations, the apparent size of this ruler depends on the geometry. If you measure the baryon acoustic oscillation scale at various distances and compare the observed angular size with the known physical size, you get another independent measurement of curvature. The result agrees with the CMB. The universe is flat. This gives us two completely independent lines of evidence pointing to the same conclusion. The angular scale of the CMB fluctuations and the physical scale of the baryon acoustic oscillations both point to a flat universe with omega equal to 1. These are different observations, made with different instruments, at different distances, using different techniques. And they agree. That's powerful. Now let's talk about expansion and fate in more depth. Because the geometry matters not just for interpreting what we see now, but for understanding what happened in the past and what will happen in the future. In the 1920s and 30s, when Friedmann and others first worked out the solutions to Einstein's equations for a homogeneous universe, the picture was elegant and simple. The universe is expanding, and the rate of expansion changes over time because the gravitational attraction of matter pulls everything back, decelerating the expansion. In a positively curved universe, there's enough matter to eventually halt the expansion and reverse it, leading to collapse. In a flat universe, expansion slows towards zero, but never quite stops. In a negatively curved universe, expansion slows, but always retains some residual speed, continuing forever. For most of the 20th century, cosmologists tried to measure two numbers: the current expansion rate, called the Hubble constant, and the deceleration parameter, which describes how quickly the expansion is slowing down. They expected to find deceleration, the universe gradually breaking under the gravitational pull of its own contents. The only question was, how much deceleration? Enough to reverse the expansion? Or not quite? In 1998, two independent research teams delivered one of the most shocking results in the history of science. The Supernova Cosmology project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, studied a particular type of stellar explosion called a Type 1a supernova. Type 1a supernovae are useful because they all have roughly the same intrinsic brightness, which makes them excellent distance indicators. By comparing the observed brightness of a Type 1a supernova with its known intrinsic brightness, you can calculate how far away it is. And by measuring the redshift of the host galaxy, you can determine how fast it's moving away from us. By studying dozens of distant Type 1a supernovae, both teams measured the relationship between distance and recession speed across billions of light years and billions of years of cosmic history. They expected to find that the expansion was decelerating, slowing down over time as gravity pulled on everything. Instead, they found the opposite. The expansion is accelerating. Distant supernovae are farther away than they should be in a decelerating universe. The expansion isn't slowing down, it's speeding up. This was extraordinary. Nothing in the standard matter and radiation-only cosmology predicts accelerating expansion. Matter and radiation create gravitational attraction. They pull things together. They slow expansion down. To make expansion accelerate, you need something with a completely different gravitational character, something that pushes space apart rather than pulling it together. That something is dark energy. Dark energy is a form of energy with a remarkable property. It has negative pressure. In general relativity, both energy density and pressure contribute to gravity. Ordinary positive pressure adds to gravitational attraction, but negative pressure does the reverse. If the negative pressure is large enough relative to the energy density, the net gravitational effect is repulsive. Dark energy has exactly this property. Its negative pressure is so large that it dominates its energy density, producing a net repulsive gravitational effect that accelerates the expansion of space. The simplest form of dark energy is the cosmological constant, a term Einstein himself introduced into his equations in 1917 and reportedly later called his greatest blunder, though historians debate whether he actually said this. Einstein added it to make the universe static, because at the time everyone assumed the universe was neither expanding nor contracting. When Hubble discovered expansion in 1929, the cosmological constant seemed unnecessary, and Einstein abandoned it. But it came back. The cosmological constant represents a constant energy density of empty space itself, a property of the vacuum. If the vacuum has energy, and that energy has the right kind of negative pressure, it drives accelerating expansion. And the observations of 1998 and everything since are consistent with this picture. With dark energy in the picture, the simple connection between geometry and fate that the Friedmann equations originally suggested gets modified. In the original framework without dark energy, geometry and fate are the same question. A flat universe means borderline eternal expansion. A closed universe means eventual recollapse. An open universe means eternal expansion. But with dark energy, geometry and fate become partially decoupled. The geometry is still determined by the total energy density. The universe is flat because the total of matter, dark matter, radiation, and dark energy adds up to the critical density. But the fate of the universe is now dominated by dark energy, rather than by geometry alone. Even if the universe were slightly positively curved, with omega just barely above 1, dark energy would still drive eternal accelerating expansion. The slight positive curvature would make parallel light beams converge very gently, and in a dark energy-free universe, that curvature would eventually cause recollapse. But dark energy pushes so hard that it overwhelms the gentle pull of positive curvature. The universe accelerates outward regardless. So in our actual universe, the geometry is flat, omega equals 1, and dark energy drives eternal acceleration. The expansion will continue forever, getting faster and faster. Galaxies beyond our local group will recede from us at ever-increasing speeds. Many distant galaxies are already receding faster than light, not because the galaxies themselves are moving through space faster than light, but because space itself between us and them is expanding so rapidly that the total rate of increase in distance surpasses light speed. We can still see those galaxies today because the light we're receiving left them long ago, when conditions were different. But the accelerating expansion creates an event horizon, a boundary beyond which any light emitted now will never reach us, no matter how long we wait. As that horizon tightens, galaxies will cross it and vanish from our observable universe, one by one, their final photons stretched to infinite wavelength. Eventually, we'll be left in a vast, empty darkness, our local group of galaxies alone in an otherwise black sky. This is the long-term fate that geometry and dark energy together dictate. A flat universe with dominant dark energy doesn't recollapse. It doesn't coast to a gentle halt. It accelerates into isolation and emptiness. But there's another way geometry matters that has nothing to do with the far future. It matters for how structures form and evolve in the universe right now. The rate at which structures grow, the speed at which gravity pulls over-dense regions together to form galaxies and clusters, depends on the geometry and composition of the universe. In a universe with more matter and positive curvature, gravity pulls harder, structures form faster, and the cosmic web develops more quickly. In a universe with less matter and negative curvature, gravity is weaker relative to expansion, structures form more slowly, and the cosmic web is more diffuse. In a flat universe with the measured amounts of matter and dark energy, structures form at a specific rate that we can calculate and compare to observations. Galaxy surveys that map millions or billions of galaxies across the sky measure this growth rate. They measure how clustered galaxies are at different cosmic epochs, how the clustering has evolved over time, and how the statistical properties of the cosmic web compare to theoretical predictions. These measurements are sensitive to both the geometry and the dark energy content, and they provide yet another independent check on the cosmological model. The agreement between all these different observations, the CMB fluctuation sizes, the baryon acoustic oscillation scale, the supernova distances, the growth rate of structure, the galaxy clustering statistics, is one of the great triumphs of modern cosmology. All of them point to the same model: a flat universe with about 5% ordinary matter, 27% dark matter, and 68% dark energy. This model is called lambda CDM, where lambda represents the cosmological constant, CDM stands for cold dark matter, and it is currently the standard model of cosmology. It fits essentially every large-scale cosmological observation we have, and the geometry, the flatness, is central to the whole thing. If the universe weren't flat, none of the other numbers would fit. The CMB peaks would be in the wrong positions. The baryon acoustic oscillation scale would appear at the wrong angular size. The supernova distances would be inconsistent. The growth of structure would proceed at the wrong rate. Everything hangs together precisely because the geometry is flat and the composition is what it is. Change any piece and the whole framework falls apart. That's what makes the geometry of the universe so much more than an abstract curiosity. It's the foundation on which all of observational cosmology is built. Every distance measurement, every age estimate, every calculation of how much matter the universe contains, all of it assumes a specific geometry. The flatness of space isn't just a fact about the universe, it's the scaffolding that supports our entire understanding of the cosmos. But flatness itself is surprising, deeply surprising. It requires explanation. Because if you trace the history of the universe backward, flatness becomes increasingly unlikely unless something specific happened in the very early universe to make it so. A flat universe isn't the default. It's a razor-thin target, and the fact that the universe hit it with such precision demands an answer. That's what we'll explore next, along with questions that go even deeper. Is the universe truly infinite? Does it have a shape beyond curvature? And how much of reality might be permanently hidden from us by the geometry of space itself? So the universe is flat. The cosmic microwave background tells us so. The baryon acoustic oscillations confirm it. The supernova distance measurements agree. Every major line of cosmological evidence converges on the same answer. Omega equals 1, to extraordinary precision. The total energy density of the universe matches the critical density almost exactly. The geometry is Euclidean on the largest scales. Parallel light beams stay parallel across billions of light years. Triangles drawn with light spanning the observable universe have angles summing to 180 degrees. Space, on average, behaves precisely the way your high school geometry teacher said it should. And this is a problem. Not because flatness contradicts anything, it doesn't. Flatness is perfectly consistent with general relativity, with observations, with everything we know about physics. The problem is that flatness is unstable. It's not a condition the universe naturally maintains. It's a condition the universe naturally drifts away from. And the fact that the universe is still flat after nearly 13.8 billion years of expansion requires explanation. Here's why. In a universe filled with matter and radiation, the value of omega, the ratio of actual density to critical density, changes over time. If omega starts even slightly above 1, even by the tiniest fraction, it grows. The positive curvature increases. The universe becomes more and more closed as it evolves, pulling farther and farther from flatness. If omega starts even slightly below 1, it shrinks. The negative curvature increases. The universe becomes more and more open, again pulling away from flatness. Omega equal to 1 is an unstable equilibrium. It's like balancing a pencil on its tip. Any deviation, no matter how small, gets amplified over time. The pencil falls. Omega moves away from 1. But here's the extraordinary thing. The universe has been expanding for nearly 13.8 billion years, and omega is still indistinguishable from 1. It hasn't drifted. It hasn't fallen off the knife edge. After all that time, all that expansion, all those billions of years during which any initial deviation should have been amplified enormously, the universe is still balanced. If you run the calculation backward, you can ask how precisely omega must have been tuned at the beginning for it to still be this close to 1 today. The answer is staggering. At 1 second after the Big Bang, omega must have been equal to 1 to within about 1 part in 10 to the 15th, 1 part in a quadrillion. At the Planck time, roughly 10 to the negative 43 seconds after the Big Bang, the required precision is even more extreme, perhaps 1 part in 10 to the 60th or beyond. The initial conditions must have been fine-tuned to an almost inconceivable degree. This is called the flatness problem, and it's not a problem with the data. The data are clear. The universe is flat. The problem is explaining why. What physical mechanism could have set the initial conditions with such absurd precision? Saying the universe just happened to start that way is not a satisfying answer. In physics, when you encounter extreme fine-tuning, you look for a mechanism. The mechanism most physicists believe provides the answer is cosmic inflation. Inflation is a hypothetical period of extraordinarily rapid expansion in the very early universe. The idea was first proposed by Alan Guth in 1980 and independently developed by Andre Linde, Paul Steinhardt, and others in the early 1980s. The core concept is simple. Very early in the universe's history, perhaps around 10 to the negative 36 seconds after the Big Bang, a brief episode of exponential expansion occurred. During this period, the universe expanded by an almost incomprehensible factor in an incredibly short time, far faster than the ordinary expansion that followed. This exponential expansion does something powerful to the geometry. Think about a balloon with wrinkles and bumps on its surface. If you inflate it to an enormous size, any small patch of the surface becomes extremely smooth and flat. The curvature doesn't disappear. The balloon is still a sphere, but any region small enough relative to the total size of the inflated balloon looks indistinguishable from flat. The curvature is stretched away. Whatever curvature existed before inflation is diluted by the expansion until it becomes unmeasurably small within any observable patch. Inflation does the same thing to the universe. Whatever the initial curvature was, however far omega was from 1 before inflation, the exponential expansion drives omega so close to 1 that the residual deviation is undetectable. It doesn't matter whether the universe started positively curved, negatively curved, or anything in between. After enough expansion, the observable universe, the region we can actually see, is so small compared to the total that it looks flat. Inflation makes flatness inevitable rather than miraculous. It replaces extreme fine-tuning of initial conditions with a dynamical mechanism that produces flatness automatically. But what actually drives inflation? What makes the universe expand so violently in that first fraction of a second? The answer involves a concept from quantum field theory, a field trapped in the wrong energy state. In physics, a field is something that has a value at every point in space. An electromagnetic field, for example, has a strength and direction at every location. The inflationary mechanism involves a hypothetical field called the inflaton field. In the very early universe, this field was in a high-energy state, what physicists call a false vacuum. A false vacuum is a state that appears stable, but isn't truly the lowest energy configuration. Think of a ball resting in a shallow dip on the side of a hill. The ball seems settled, it's not moving, but it's not at the bottom of the hill. There's a lower energy state available if the ball could somehow get out of the dip and roll further downhill. While the inflaton field is stuck in this high energy state, something remarkable happens. The energy stored in the field behaves like a cosmological constant. It has a huge energy density, and critically, it has enormous negative pressure. This combination produces a repulsive gravitational effect that drives space apart with incredible force. The expansion is exponential. Every tiny fraction of a second, the universe doubles in size, then doubles again, then again. In roughly 10 to the negative 32 seconds, the universe expands by a factor of at least 10 to the 26. That's the minimum. Many models predict far more expansion. In some scenarios, a region smaller than a proton could inflate to a volume vastly larger than the entire observable universe today. Eventually, the inflaton field decays. It rolls out of its false vacuum state toward the true vacuum, the actual lowest energy configuration. As it does, the enormous energy stored in the field is released. It converts into a flood of particles and radiation, filling the newly expanded space with matter and energy. This is reheating, and it produces the hot, dense plasma that we think of as the Big Bang. The exponential expansion stops, and the universe transitions to the slower, decelerating expansion governed by the gravity of all the matter and radiation that was just created. So inflation isn't magic. It's driven by a field with stored energy that creates repulsive gravity. The exponential expansion is a natural consequence of that stored energy's gravitational properties. And when the field releases its energy, the universe is left flat, smooth, and seeded with the quantum fluctuations that become everything we see. This is inflation's primary achievement regarding geometry. It solves the flatness problem not by arguing that the universe is exactly flat, but by arguing that it's so close to flat within our observable region that we could never tell the difference. The universe as a whole might be positively or negatively curved, but if inflation expanded it by a large enough factor, the curvature radius is so much larger than the observable universe that we can't detect the deviation from flatness. It's like standing on Earth's surface and seeing a flat horizon. The surface is curved, but the scale of that curvature is so much larger than your visual range that flatness is all you can measure. Inflation also solves other cosmological puzzles simultaneously. The horizon problem, the question of why regions of the universe that appear to have never been in causal contact have the same temperature and density, is resolved because those regions were once close together before inflation stretched them apart. The monopole problem, the prediction from particle physics that the early universe should have produced enormous numbers of magnetic monopoles that we don't observe, is resolved because inflation dilutes the monopole density to undetectable levels. But inflation does something else that connects back to everything we discussed about structure and the cosmic microwave background. During inflation, quantum fluctuations, tiny random variations that exist in every quantum field, were stretched from subatomic scales to macroscopic and even cosmic scales by the exponential expansion. These stretched quantum fluctuations became the density variations that eventually grew under gravity to form galaxies, galaxy clusters, and the entire cosmic web. The hot and cold spots in the CMB, the baryon acoustic oscillations, the filamentary structure of the universe, all of it traces back to quantum fluctuations amplified by inflation. This means the geometry, the flatness, the density fluctuations, and the large-scale structure of the universe are all connected through a single physical mechanism. Inflation flattened the geometry, generated the fluctuations, and set the initial conditions from which everything we observe today evolved. The geometry is not just a property of the universe, it's a consequence of the universe's dynamical history. The flatness tells us something happened, something dramatic and brief and powerful in the first fraction of a second. And inflation is the best explanation we have for what that something was. Now, there's an important subtlety. Inflation predicts the universe should be very close to flat, but it doesn't necessarily predict exactly flat. If inflation lasted long enough, omega is so close to 1 that no conceivable measurement could ever detect the deviation. But in principle, the universe might have a tiny residual curvature, positive or negative, that's simply too small for us to see. The Planck satellite's measurement, as we've seen, is consistent with exact flatness, but it's also consistent with a tiny positive or negative curvature that falls within the measurement uncertainty, which is less than 0.25% in either direction. We may never know whether the universe is precisely flat or merely so close to flat that the difference is undetectable, and the distinction might not matter physically. If the curvature radius is vastly larger than the observable universe, the effects of curvature would never manifest within our cosmic horizon. For all practical purposes, the geometry we experience is flat, regardless of whether the universe as a whole is exactly flat or merely very nearly so. But there's a deeper question lurking here, one that most discussions of the shape of the universe overlook entirely. and it has to do with the difference between geometry and topology. Geometry tells you about curvature. It tells you the local rules that govern distances, angles, and volumes. It tells you whether parallel lines converge, diverge, or stay parallel. But geometry does not tell you about the overall structure of space. It doesn't tell you whether the universe is finite or infinite. It doesn't tell you whether space connects back to itself or extends forever without repetition. These are questions about topology, and topology is a separate property from curvature. Here's an example that makes the distinction clear. Take a flat sheet of paper. It has zero curvature. Euclidean geometry holds everywhere on its surface. Now take that flat sheet and roll it into a cylinder. The geometry is still flat. Curvature hasn't changed. An ant living on the cylinder could draw triangles, measure angles, and find they sum to exactly 180 degrees. Parallel lines on the cylinder remain parallel. All the local geometric tests say flat. But the topology has changed. On the flat sheet, if you walk in one direction, you go on forever without returning. On the cylinder, if you walk around the circumference, you come back to where you started. The space is still flat, but it's no longer simply connected. It wraps around in one direction. Now go further. Take the cylinder and connect its two ends, bending it into a donut shape called a torus. The geometry on the surface of an ideal torus can be made flat. This seems counterintuitive because a physical donut sitting in three-dimensional space has curvature. But if you imagine building the torus by taking a flat square and identifying opposite edges, gluing the top to the bottom and the left to the right, the resulting surface has flat geometry everywhere. It's finite, it has a definite area, but it has no boundary and no edge. And its geometry is perfectly flat. This means a flat universe doesn't have to be infinite. A flat universe could be finite if it has the topology of a three-dimensional torus or some other compact flat space. You could travel in a straight line and eventually return to your starting point, not because space is curved, but because space wraps around in certain directions while remaining geometrically flat everywhere. The curvature is zero, but the topology connects distant regions. This is a genuine physical possibility. General relativity tells us the geometry. It tells us the curvature, but it doesn't uniquely determine the topology. Einstein's equations are local equations. They describe how curvature relates to energy and matter at each point in space. But many different topologies are consistent with the same local geometry. A flat, infinite universe and a flat, finite torus both satisfy the same local equations. You need additional information to determine the topology. Can we test this? In principle, yes. If the universe has a compact topology, meaning it wraps around in one or more directions, there would be observable consequences. Light traveling around the universe would create repeating patterns. If you looked far enough in one direction, you'd eventually see the same structures you see in another direction, because you'd be looking all the way around the universe and seeing the back of your own cosmic neighborhood. The cosmic microwave background would show correlated patterns at large angular scales, matching circles or other features that correspond to the wrapping scale. Cosmologists have searched for these patterns. They've analyzed the CMB data from both WMAP and the Planck satellite, looking for signatures of compact topology. So far, no convincing evidence has been found. The universe appears to be simply connected on scales up to the size of the observable universe, roughly 46.5 billion light-years in radius. If the universe does wrap around, it does so on a scale larger than what we can observe. The topology, if it's non-trivial, is hidden beyond our cosmic horizon. But imagine for a moment what it would actually be like to live in a universe with compact topology. Suppose the universe were a three-dimensional torus, flat everywhere but wrapping around in all three spatial directions with a circumference of, say, 20 billion light-years. What would you see? You'd see copies. light leaving a distant galaxy would travel through space, reach the boundary where space wraps around, and continue from the other side. It would arrive at your telescope from a completely different direction than the original galaxy. You'd see the same galaxy in two different parts of the sky. If the wrapping distance were short enough relative to the observable universe, you'd see multiple copies of the same structures, the same galaxy clusters appearing again and again, viewed from different directions and at different times in their history, because the light for each copy traveled a different total distance. The cosmic microwave background would carry an especially distinctive signature. The surface of last scattering, the shell of ancient light surrounding us, would intersect itself if the universe wraps around on a scale smaller than the distance to that surface. Where the shell intersects, you'd see matched circles, pairs of circles in the CMB sky with identical temperature patterns. The circles would appear in different parts of the sky, but their temperature sequences would match because they correspond to the same physical location in space, seen from two directions because light wrapped around the universe. This is a specific, testable prediction. Cosmologists have searched the CMB data for these matched circles with great care. The analysis is demanding because you're looking for subtle correlations across the entire sky, and noise and foreground contamination can obscure weak signals. But the searches have been thorough, and no matched circles have been found at scales within the observable universe. This doesn't prove the universe has trivial topology. It proves that if the universe wraps around, it wraps on a scale larger than roughly the diameter of the observable universe. The repeating patterns, if they exist, are beyond our horizon. The copies of familiar galaxy clusters, if they're out there, are too far away for their light to have reached us. This is a profound limitation. The observable universe is finite. We can only see as far as light has traveled since the Big Bang, accounting for the expansion of space. Beyond that horizon, we have no information. We cannot see what's there. We cannot measure it. We cannot determine the topology of regions we can't observe. And this means we may never know whether the universe is finite or infinite. We may never know its full shape. We're like creatures living on a vast plain, able to see to the horizon in every direction, knowing the ground beneath our feet is flat, but unable to determine whether the plain extends forever or wraps around on itself just beyond the limits of our vision. This connects to something even more fundamental. The geometry we measure, the flatness we observe, applies only to the observable universe. It's a statement about the 93 billion light-year diameter region we can probe. It says nothing definitive about what lies beyond. The universe could be flat everywhere, stretching infinitely in all directions. It could be flat within our observable region, but gently curved on much larger scales, so that the full universe is actually closed, finite, and wrapping back on itself with a curvature radius vastly larger than our horizon. We can't tell the difference. Inflation makes this situation worse, or better, depending on your perspective. If inflation expanded the universe by a factor of 10 to the 26th or more, the full universe is enormously larger than the observable region. The observable universe would be like a speck on the surface of an incomprehensibly large balloon. The curvature of the balloon is real, but no measurement within the speck could detect it. The speck looks flat because the curvature scale dwarfs it completely. Some inflation models predict the universe expanded by far more than the minimum needed to solve the flatness and horizon problems. In eternal inflation scenarios, the inflationary process never completely stops. Different regions stop inflating at different times, each one becoming a separate pocket universe with its own properties. The total inflating space grows without limit, spawning pocket universes endlessly. In this picture, our observable universe is one pocket in an infinite or near-infinite inflationary landscape, and the question of the full universe's shape becomes almost unanswerable. Each pocket might have its own effective geometry, its own topology, its own local physics. The larger structure might have no single well-defined shape at all. This is speculative. Eternal inflation is a theoretical prediction of certain inflation models, not an observational fact. But it illustrates how much of reality might be permanently beyond our reach. The geometry we measure tells us about the cosmos we can see. It's silent about what we can't. Let me now address the question that most people actually want answered when they ask about the shape of the universe. Does the universe have an edge? The answer, as far as we can tell, is no. A flat, infinite universe has no edge by definition. It extends forever in every direction. There's no wall, no boundary, no place where space stops and something else begins. A positively curved, finite universe also has no edge. It wraps around on itself like the surface of a sphere, finite but unbounded. You can travel forever without reaching an end. Even a flat, finite universe with non-trivial topology has no edge. The torus wraps around. There's no boundary. You simply return to where you started. The concept of an edge only makes sense if the universe is embedded in something larger, if there's an outside for the edge to separate from. But as we discussed at the very beginning, the universe is not inside anything. There is no outside. The universe is all of physical reality. The question of what's beyond the edge doesn't apply because there is no beyond. There's nothing for an edge to border. This is one of the hardest things for human intuition to accept. We're wired to think of finite things as having boundaries. A room has walls. A lake has shores. A country has borders. But the universe, if it's finite, has no boundary. It's like the surface of a sphere. The surface has a finite area, but an ant walking on it never encounters an edge. There's no line beyond which the surface stops existing. The surface simply curves back on itself, every direction eventually leading back to where you started. People sometimes ask what the universe is expanding into. If the universe is expanding, there must be something outside it that it's expanding into, right? No. Expansion doesn't mean the universe is getting bigger inside some pre-existing space. Expansion means the distances between objects within the universe are increasing. Space itself is stretching. New space is being created between galaxies, not because the galaxies are moving outward into something, but because the fabric of space between them is growing. The universe isn't expanding into anything. It's just getting larger in the sense that internal distances are increasing. Now let me step back and think about what all of this really means. What does the shape of the universe tell us about our place in it? The geometry of the universe is flat. This means space, on the largest scales, follows the simplest possible set of rules. Parallel lines stay parallel. Triangles are normal. Volumes scale the way Euclid said they should. There's no exotic curvature bending space into strange topologies or forcing the universe toward eventual collapse. The cosmos is geometrically simple, even if its contents are complex. The flatness is not a coincidence. It was produced by inflation, a brief period of explosive expansion that smoothed out whatever initial curvature existed and set the universe on its current trajectory. Inflation also generated the density fluctuations that eventually became every galaxy, every cluster, every filament in the cosmic web. The flatness and the structure are two faces of the same coin, both produced by the same mechanism in the first fraction of a second after the Big Bang. The flatness, combined with the dominance of dark energy, determines the universe's fate. The expansion will continue accelerating forever. Galaxies beyond our local group will gradually disappear beyond the cosmic horizon. The sky will darken. The universe will become increasingly empty, cold, and silent over the eons. Stars will burn out. Matter will decay. Eventually, in the unimaginably distant future, the universe will approach a state of maximum entropy, a near-perfect void with no structure, no complexity, no activity. This isn't speculation. It follows directly from the measured geometry and composition, from the flatness and the dark energy. But there's something else the geometry tells us that is perhaps more important than any prediction about the far future. It tells us the limits of our knowledge. The The observable universe is finite. We can see about 46.5 billion light-years in every direction. Beyond that, the universe continues, but we have no access to it. We cannot see it, measure it, or interact with it. The geometry within our observable horizon is flat, but we have no information about the geometry beyond it. The universe could be infinite. It could be finite. It could wrap around in ways we'll never detect. The full shape of the cosmos might be permanently unknowable. This is a humbling realization. Science has taken us extraordinarily far. We've measured the curvature of space to a precision of 0.5%. We've determined the composition of the universe to a few significant figures. We've traced the history of cosmic expansion back to fractions of a second after the Big Bang. We've connected quantum fluctuations in the infant universe to the distribution of galaxies across billions of light-years today. These are among the greatest intellectual achievements in human history. And yet the full answer to the simplest-sounding question, what shape is the universe, might lie forever beyond our grasp. We know the local geometry. We know the curvature. We know it's flat within our observable region. But the global topology, the full structure of space on scales we can never observe, remains unknown and perhaps unknowable. Physics tells us what kind of universe we inhabit. It tells us the rules that space follows on the largest scales we can probe. It tells us those rules are flat, Euclidean, simple. But it also tells us that this flatness is a product of specific physical processes that occurred in the first instant of cosmic history, and that the simplicity we observe might be local, a feature of our patch, not a statement about the cosmos in its entirety. The shape of the universe matters because geometry controls everything: how light travels, how structures form, how expansion proceeds. What kind of future is possible? Without knowing the geometry, we couldn't interpret a single observation of the distant cosmos. The flatness of space is the foundation of modern cosmology, the scaffolding on which our entire picture of the universe is built. But the shape of the universe also matters because of what it reveals about the nature of knowledge itself. We are small creatures on a small planet, looking outward at a cosmos that is almost certainly vastly larger than the part we can see. We've learned an enormous amount using nothing but light, gravity, and mathematics. We've figured out the geometry of space from within, without ever stepping outside, exactly as Gauss and Riemann showed was possible 2 centuries ago. We've measured the curvature of the universe using the same principles that a 2-dimensional creature could use to measure the curvature of its surface. We've reached outward with our instruments and our intellect, and grasped something that seemed impossible to grasp. And yet we've also discovered boundaries. Hard boundaries imposed by the speed of light and the age of the universe. The observable universe has a horizon. Beyond it lies more universe, perhaps infinitely more, that we cannot see and cannot study. The geometry of that unseen cosmos might be different from what we measure here. The topology might be surprising. There might be structure and complexity out there that we will never know about. The universe gave us enough information to determine its local geometry with remarkable precision. But it also placed a fundamental limit on how much further we can go. The shape of the universe, in its full and complete sense, might be the ultimate question that physics can pose but never fully answer. Not because we lack cleverness or instruments, but because the universe itself, through the finite speed of light and the structure of space-time, has drawn a boundary around what any observer, anywhere, can ever know. That's what the shape of the universe really tells us. It tells us the rules of the cosmos we inhabit. It tells us the fate that awaits everything within it. And it tells us, with quiet finality, that there is always more universe than we can see. The geometry is flat. The future is eternal expansion. And the full shape of reality extends beyond our horizon. vast and silent and unknown.